Yes, hope all of us are doing fine. My name is Ernest and this is Ernest Sciences and Mathematics TV channel. In this particular video, I'm going to look at the concept of an ideal gas of diatomic molecule, and this is going to form the last bit and the third part of the discussion on the rotational partition function of a diatomic molecule. Now, in our previous videos, we had looked at various aspects of representing this rotational aspect of a diatomic molecule, and of course, we had decided we're going to consider a various number of factors, especially on the a moment of inertia and the distance from the center of mass. And of course, in trying to describe the concept of rotational or allowed energies, we had used the concept of the Schrodinger's equation in trying to give that rotational aspect of energy. And that generally gave us the general description of a rotational partition function of a diatomic molecule represented by this specific equation, which we gave in terms of the summation of this of course, values for j from 0 to infinity, whereby we see that this j is going to represent the rotational quantum number, and of course this gave us values of also 2j plus 1, whereby we see that 2j plus 1 is going to represent the degeneracies, and this one was given in terms of the exponent of specific values for the negative j into j plus 1. And of course, this was a derivation from the Schrodinger's equation by substitution of energy, and we considered the aspect of rotational temperature. So this was given as a division by T, and then we had the rotational temperature given at that specific end. So in this case, this aspect of rotational temperature, as we said, was the ratio between, of course, these specific quantities, whereby we had this one representing 8 pi squared, the moment of inertia k be given as such, and that of course, as we said, is going to be of course a collection of specific constants which are going to be having the combined unit of the Kelvin scale, and of course that one gave us a general description for the rotational partition function. Now, one of the aspects or the importance of this specific rotational temperature which I mentioned was that it can assist us to describe whether a molecule is going to exhibit classical or quantum behavior, in a sense that if a molecule is going to be exhibiting a behavior whereby the change in energy, which is a delta U given as that one, is much smaller than the value of kBt, this is going to imply that the temperature T is going to be much greater than the rotational temperature, and therefore this molecule is going to be described as exhibiting a classical behavior. And in our treatment of this specific equation, and therefore we're going to do an integration over this specific of course range of values in order to obtain the value for the of course the rotational quantum of course number which we have written above. So in case the value for energies for this specific delta U are much smaller or much greater than the value of kBt, this is going to imply that the temperature T is going to be much smaller than the rotational temperature, and this is going to imply a concept of summation, which is going to basically be giving the concept of quantized behavior, and therefore we're going to have so this molecule is going to be of course display the concept of quantum behavior given as such. And I've mentioned the concept of summation and the integration in these two specific states of the quantum and the classical behavior from my initial discussion. Now, of course, we're going to look at this specific aspect by trying to replace this specific summation sign by integration, and trying to see whether we can find a standard way of trying to express this partition function in a more, of course, elaborate way. Now, in this case, we're going to consider a case whereby we're going to do a substitution of some specific components which we're going to consider in this particular equation. Now, this is going to assist us replace, of course, this particular summation sign by the integration sign, and this is going to assist us in some cases we have mentioned about of course, in trying to find a way of using the standard integral. Now, let's try to do a replacement and see what kind of equation we're going to come up with, and of course we will elaborate on its basic significance. So in this case, I'm going to do a substitution for the values of x for the values of the which are contained in this equation, which are j into j plus 1. And therefore, this particular set of the equation is going to be represented by j. And therefore, I'm as well going to do a replacement for the values of put in place the value of dx to represent values of this degeneracy given as 2j plus 1 times, of course, the value of dj given as such. So this is going to assist us in doing an integration of this particular equation, and therefore we're going to have this rotational function represented as the integral between 0 and infinity for these two ranges of j, and we shall have this one given as a degeneracy of 2j plus 1, and we're going to have this exponent of negative j into j plus 1. And of course, that's going to be all over T times the rotational temperature, which might be given in terms of this particular value. And this is going to be, of course, given together with that value of dj. So in this case, we are going to see that if I may write this one by doing a substitution for these specific values. So remember, we're going to have this dx being represented by this specific component and the dj, which has just been included in this particular equation. And then we're going to have the values of x replacing the j into j plus 1 t, and therefore this version of the equation is going to be given in terms of the rotational partition function is equivalent to the integral between 0 and infinity, and this is going to be the exponent of the negative value of rotational temperature over t, and this is going to be times the value of dx given as such. So this is going to be a reduced form of this particular equation. And is this going to assist us in trying to find an integral part of this specific equation, which is going to give us, of course, a solution for rotational partition function. So therefore, this can be given, performing an integration, this can be given in terms of q r is equivalent to the values between t all over the rotational temperature. And of course, that's going to be given as. So from the laws of exponents and of course natural logarithms, we're going to see this one being given as that specific acting as a coefficient in front of this specific exponent, and of course we're going to have these other values being maintained for the negative rotational temperature over t given as such, and of course that also is going to be multiplied by the exponent of this specific rotational temperature all over t given as such, and all of that one is going to be substituted between the values of 0 and positive infinity given as such. Now if we try to substitute the limits which we are going to have for 0 and infinity, these are going to give us the product which is going to be representing the final aspect of the rotational partition function, which is basically going to be given in terms of so I can just have this one summed up. So we're going to have this particular equation reducing to a form of equation which we're going to have given as the rotational partition function is equivalent to the ratio between T and the rotational temperature given as such. And that's going to form our final bit of this representation for the rotational partition function of a diatomic molecule. So in this case, as this one has been a lengthy process, I'd like to encourage our members to check our description box so that there are other videos which you have already done preceding this one, so that you can be able to follow up on the various representations of this particular aspect of the partition function for the diatomic molecule. Now in our specific descriptions, of course, we're also going to be using the relationship from these videos in trying to evaluate other aspects of the partition function, especially concerning the aspect of a diatomic molecule. So kindly subscribe to our channel and also engage us in the comment section for more. So that is it for now, guys. Bye, God bless you. Catch us in our next video.